I am unmuted, and that's good. Thanks, Ben, and for introducing me, and thanks to the organizers for putting this together, Ivan, Noel, and Kitty. It's a great opportunity to speak. So today I'll talk about Khinchine's theorem on fractals, and this is based on joint work with Manuel Luethi. He's a postdoc in Tel Aviv. So let's start by recalling what the usual Khinchine theorem is. Also, I should say, don't be alarmed by the number of slides. I'm not going to go through all that. I'm not going to also be able to tell you much about the proof. But if you're intrigued enough, I'll be available in the breakout rooms afterwards. Khinchine's theorem is about approximation of real vectors in Rn by rational vectors. And it asks how common or how prevalent is the set of points which is approximated by a certain quality of approximation, depending on the denominator. And we measure the quality of approximation using a function that we'll call psi throughout the talk. And Khinchine theorem, which was proved about almost 100 years ago now, it involved a few more conditions, but this is the form we have nowadays. It tells us that there is a very simple way of knowing how prevalent the set of approximable vectors by quality psi. We'll refer to it as W psi throughout the talk. Given by looking at the convergence or divergence of a certain series. So this theorem, it mirrors the sort of classical Borel-Cantelli lemma, because somehow these sums correspond to the Lebesgue measure of the boxes centered around the rationals with denominator q, and say contained in the unit cube. And so the convergence part in this case is automatic, and maybe a little bit more work is needed for the divergence. Maybe some work is needed for the divergence part of it, where the series actually diverges. And an example maybe familiar to some of you is given by an example of an approximation function is the function which assigns to q 1 over q to a certain power, depending on RD. If you're working in RD, it will be 1 over d plus epsilon. And if you take all those vectors which are can be approximated with this quality of approximation infinitely often, then this set is referred to as the very well approximable vectors. All right. So my concern today will be with Mahler's question, is motivated by Mahler's question about what happens when I change the Lebesgue measure, switch the Lebesgue measure in the statement of Khinchine's theorem with some other measure. And Mahler asked sort of and perhaps an intentionally vague question. I don't know Mahler personally, so I don't know if that was intentional. He asked, how well can we approximate, say, elements on the middle third Cantor set by rational numbers, which either lie, he phrased it as two separate questions, either rationals which are on the set or rationals which are in general, not necessarily on Cantor's set. And these turn out to be sort of two completely different questions, and I will be concerning myself with the second one, which is how well can we approximate rationals, irrational points on a Cantor set or on a fractal by rational points. And I thought that the abstract of this paper by Mahler was kind of interesting, so I decided to share it with you. All right. So in order to state our results, so I'll just define what fractals I'm talking about today. My fractals will come from iterated function systems, and to me, an iterated function system today will be a finite collection of contracting similarities of RD. What do I mean by this? I mean you have maps which are affine maps. All they do is they contract by an amount rho I, they OI, or translate by a translation vector BI, right? And because all the maps are contraction, a version of the Banach fixed point theorem tells you that there is going to be a unique compact invariant set for this IFS. And this by invariant, we mean the set is equal to the union of its images under those maps. And for that reason, we call it a self-similar set or a self-similar fractal. And what are examples of such fractals? Well, it includes a lot of the familiar examples. For example, if you Google a fractal on Google Images, I think most of the things that will come up are self-similar fractals. But for example, if you look at Cantor's middle third set, it can be generated using the maps x goes to x over 3, or you contract by 1/3 and translate by 2/3. All right. So in order to talk about the Khinchine theorem or prevalence of psi approximable points on a fractal, we need to talk about measures. And the measures that are going to be supported in our fractals are that we'll consider today are what I call self-similar measures. And by that I mean, if you given a probability vector, finitely many positive numbers that add up to 1. Again, another version of a Banach fixed point theorem, because all the maps are contracting. It turns out there's a unique measure which is equal to a convex combination of its images under each of the maps by this probability vector. And we'll call measures which the unique measure satisfying this a self-similar measure. An example of this is the usual Cantor-Lebesgue measure that you have on a Cantor set, where you assign to each map probability 1/2.
Osama, is it okay to think of this as a stationary measure for the random walk driven by the FIs with probabilities?
Yes, that's precisely what it is. It's a stationary measure, stationary probability measure for a random walk on RD. Thank you. All right, I will ask one requirement of my measures, which is fairly mild. I will ask that the pieces of the fractal under so if I take my fractal and I map it by 2 different maps, they may overlap. And I ask that the overlap has measure 0 with respect to the self-similar measure I'm considering. So this is a fairly mild condition. It's satisfied for a lot of natural examples, but it's somehow important for our methods. And it's important in general when people think about fractals for whatever reason, to think about this overlap between pieces of the fractal. For example, this definition I just made, for all you know, 2 of the maps could be the same, and somehow we don't want that sort of thing. And more generally, you want to control the overlap that happens between 2 pieces of the fractal in some way.
Osama, you probably said this, but is it obvious that such self-similar measures exist?
So they exist because of some kind of a fixed point theorem, because all the maps are contracting. There exists a unique one determined by the IFS and the probability vector without any assumptions. Yeah, no problem. Okay, so these are my measures. With this terminology now, I can state our theorem. So you give me a decreasing quality function that measures quality of approximations, a self-similar measure on RD with null overlaps. Then we require 2 actual hypotheses now. We require that the maps in the IFS have rational parameters. So I told you they are contractions, rotations, and translations. So if you look at the matrices that you get out of these affine maps, I require that all the entries are rational. And I also require that my measures are sufficiently thick. And I will define what that means. It's a made-up word that I made up for giving talks, but it's a very simple condition. Under those 2 conditions, we obtain a complete analog of Khinchine's theorem. The same series that may converge or diverge governs the size of the psi approximable vectors, but we replace the big measure with a self-similar measure on a fractal. So I should point out, so this is, to the best of my knowledge, this is the first sort of generalization of Khinchine's theorem, which is a complete sort of a complete analog where you just completely replace Lebesgue measure with a new measure, which is, in general, singular with respect to Lebesgue. Moreover, something to keep an eye out here for is that the series that we ask converges or diverges is the same series as in the Lebesgue case. Well, the reasoning for the Lebesgue case was that, well, this psi to the d measures gives you the Lebesgue measure of boxes centered around rationals. So there was at least a reason to expect that this is sort of what the form should be. But as far as I understand, I don't think there was an expectation of what a Khinchine theorem should look like. And certainly if you had asked me 2 years ago before we started working on this project, I'd have told you for sure there would have been something about the house of dimension of the fractal somewhere, or some mention of the fractal in the series that governs the theorem. Right. So what does a sufficiently thick mean? Well, there is a sort of a condition called the open set condition that people commonly impose on iterative function systems. And under this condition, or this sufficient thickness, the formula simplifies a lot, so we can actually put it on a slide. And it tells you the following. You have contracting maps, and their contraction ratios are rho I. I take the smallest contraction ratio, I call it rho min. I also have a probability vector, P1 through Pn, and I take the maximum entry in the probability vector, and I call that Pmax. And D is the dimension of the ambient space. And I take this ratio, and it turns out that it's bigger than 1. I compare it to 1, how much bigger than 1 it is, and I demand that it's strictly less than this explicit epsilon 0, which depends only on the dimension of the ambient space. And it's very explicit. We have a formula. Yeah. In nice examples that people like to think about, so this epsilon 0 is small, so we don't answer Mahler's question. We don't do we can't handle Cantor's middle third set, so no false advertising. Don't go suing me. But if you can think about, so Cantor's middle third set concerns the set of points in the middle in the unit interval whose triadic expansion does not include the digit 1. But you can think about, well, what about missing digit sets for other expansions? So expansion mod, say, to the base 107 or something like that. If you're not missing too many digits, then if you require you're only missing a few digits and the base is sufficiently big, then you fall under our theorem. Khinchine theorem will hold for such a set. And then more generally, if all the contraction ratios are the same and all the probability all the entries in the probability vector are the same, then being sufficiently thick is equivalent to asking that the house of dimension is sufficiently close to being full. So that's a good mental picture to keep in mind. And because it's a made-up word, but it may overlap with some people's terminology, when I say sufficiently thick, in all cases, the support of our measure has 0 Lebesgue measures. So there's nothing that follows from known results. All right, so I just gave you a statement about how to intersect some Diophantine set with a fractal. Well, where did this come from? Where did this kind of question come from? So I'll just try to give you some brief history. So in the 1930s, Mahler was thinking about problems of approximating algebraic numbers by rationals. And that turned out to be related to understanding the measure of very well approximable vectors on certain submanifolds of Rn. And because of this connection, in the period from the 30s to the 60s, several people formulated conjectures about how prevalent very well approximable vectors are with respect to a volume measure on some submanifold of Rd. And non-degenerate here means if your submanifold is analytic, it just means that the manifold knows that it's in Rd. So it's not contained in any proper affine subspace. That's all that means.
Can I ask a silly question?
Yes, please go ahead.
So you're talking about algebraic numbers being very well approximable.
No. So in understanding approximation of algebraic numbers, you are led to a corresponding problem about approximating points on manifolds, which are for a particular manifold, which is x squared up to x to the n, if you're thinking about algebraic numbers of degree to the n, and asking about the prevalence of those turns out to tell you something about algebraic numbers on the real line.
Okay, thanks.
And so this theory somehow of studying Diophantine approximation on manifolds somehow led to an explosion of literature, and a turning point was the work of Kleinbock and Margulis, who resolved a lot of the previous conjectures. about very well approximable vectors, which led to people thinking about, well, what about Khinchine theory? Because very well approximable vectors were thinking about the particular quality of approximation, the particular psi. And there's a lot of literature. I just listed quite a few names here. But this study motivated a lot of people to think about, well, what's so special about manifolds? Maybe we can think about measures on Rn, and we can think about the prevalence of any given Diophantine property in Rn with respect to something that's not the Lebesgue measure. So for example, a measure on a manifold or a fractal, as we're thinking, or subspaces, affine subspaces, and so on. And turns out that somehow, sometimes when you understand something in one context, it sheds light on other contexts. But specifically for fractals, there was an influential paper by Kleinbuch and Linden, Strauss, and Weiss in 2004 and early 2000s, and later strengthened by Poynton and Villani, where they proved that for a very wide class of measures, which includes the fractals we talk about today, it includes manifolds, it's a very wide class of measures. If the approximation function has a convergent series, but moreover, it converges quickly enough, then the points who are psi approximable are not prevalent with respect to any of this large class of measures. All right? And naturally, they asked, well, do we expect something like a Khinchine theorem to hold for such measures? And in fact, Poynton and Villani wondered whether their results were optimal in dimension one, meaning they gave a series, they gave this series I have on the slide, and they said, well, if this converges, then the W psi has measure 0. Well, what happens when it diverges? They asked whether you should expect a full measure. And what we do, our result tells us that we give a positive answer to the first question and a negative one to the second one for the fractals we handle. Right. Okay, so this is an ergodic theory seminar or dynamics sort of conference. And really my interest in this kind of problem came from its correspondence to dynamics and the methods that go into it, which I'm very happy that about the fact that I won't be able to tell you anything about the methods probably today. But let me give you at least the correspondence to dynamics. In order to understand dynamics of sort of Diophantine approximation or RD, it turns out that the right dynamical system to look at is a flow on a homogeneous space, which is a quotient of SLD plus 1R by the integral matrices. So this is a finite volume space, and the dynamical system will come from a particular diagonal flow, which I put on the slide. And we realize RD inside this space as orbits of the group, of the upper triangular group, where you think of points in RD as column vectors, and you put ones on the diagonal and zeros everywhere else. Okay. Now this space, this homogeneous space, has a geometric meaning. It's a space of all covolume 1 lattices in RD plus 1. And once you think of it this way, you can immediately see why it's not a compact space. So you can take a sequence of lattices, discrete subgroups of RD plus 1, where the shortest vector goes to 0. And perhaps this is the fact that this space is not compact is the fundamental reason why Diophantine approximation is a rich study. And beginning with work of Dani in the 80s, people realized that the Diophantine properties of a vector in RD are really governed by the evolution of the forward orbit under the diagonal flow of the identity coset coming from this vector X in the space G mod gamma. And in our specific situation, if you're thinking about psi approximable vectors, there's no fractals here in the slide. If you're thinking about psi approximable vectors for some quality of approximation psi, the correspondence, which was first noticed by Sullivan in the early 80s and generalized by Kleinbuch and Margulis, beyond just dimension one, higher dimensions and more generally, is that a vector is psi approximable if and only if its forward orbit visits a shrinking neighborhood of the cusp, where the rate at which the neighborhood shrinks is governed by this function psi, your quality of approximation. What is the cusp? What do I mean by the cusp? I mean the set of lattices in Rd plus 1 whose shortest vector is smaller than epsilon, and you visit such a set at a time which is also connected to epsilon. So when we understand the set this way, unfortunately, still we don't get any free lunch. We don't get either a convergence or a divergence case. Not only because it's coronavirus land and I'm not actually at the conference, so I'm not going to get a free lunch, but also because we still need to estimate the measure of the set of points which will visit some shrinking cusp at some time with respect to a fractal measure. And because we phrased it in terms of shrinking target problem, there's the set of psi-approximable vectors has a sort of a natural lim sup structure. And so you want to apply a Borel-Cantelli sort of lemma to it. So not only do you want to understand that the measures of these sets that go in the lim sup have a divergent or convergent sum, but also you want to understand that they have some independence when the series does diverge. Additionally, when you sort of first look at this problem, you're tempted, you want to count the rational points near your fractal, and you want to sort of take balls around these points and measure their, estimate their measure and so on and so forth. But the very natural thing you will notice is that, for very nice measures, fractal measures, the measure of a ball is comparable to the radius of the ball raised to the Hausdorff dimension of the fractal. Okay? But we're telling you that the convergence and divergence of the series is measured by something that has no Hausdorff dimension in it, which indicates that somehow there's a very subtle distribution of these rationals near the fractals. So we don't do that. We don't understand the distribution of the rational vectors near fractals. We go a different route. And really the main theorem that actually allows us to prove this Khinchine theorem is the following equidistribution result, effective equidistribution result, which is also new even in its qualitative form, even without the error rate. So under the same hypotheses on the fractal measure, I can realize my fractal in the homogeneous space, G mod gamma, through the orbits of this group U plus from identity. So these cosets UX, they are parametrized by RD, so I can think of my fractal as sitting there. Then I push this group by the diagonal flow, GT, that I gave you before, and I measure the set of points. I integrate a continuous function on this set of on this fractal with respect to my fractal measure. And I ask what happens as t goes to infinity. You want to think, say, this continuous function is an approximation of your cusp, say, cusp neighborhood, indicative function of the cusp. And what we give you is that this converges to the Lebesgue measure on the homogeneous space, the Haar measure, with an exponential rate of convergence. And that's what's crucial for our arguments. Because remember, the continuous functions we would like to integrate are approximations of cusps that depend on t. So you really want the rate of convergence. And what I want to make sure here is clear is that you're starting out with a measure that has no smoothness in any direction, these fractal measures, and in the limit you get a Lebesgue measure on the whole space. However, still one does not really get a free lunch, even with this theorem in hand. The error terms we give depend on the sort of the CK norms of the derivatives, which is very common when one works with these things. And that turns out to pose quite some technical difficulties when one tries to understand the divergence case of the theorem. So just throwing this out there for people to know that somehow, if you say, well, you say this is an equidistribution theorem on the whole homogeneous space, can you handle any shrinking target and get a exact sort of divergence convergence theorem for a target that's shrinking to any point, not necessarily the cusp? And the answer is no. Somehow we do need some number theoretic input to even push this to get the Khinchine theorem. All right, so a picture, because I think I should put pictures on my slides. What is going on, say, let's say in dimension 1, and let's say you have a Cantor set and you imagine, say, it's sitting on the unit interval. Well, the homogeneous space we work with is SL2R mod SL2Z. And we think of our unit interval as somehow this periodic horocycle, as a periodic horocycle. And I think if my fractal is sitting there. And as t goes to infinity, what's happening is I'm pushing this horocycle down in upper half space. And I bring it back to my fundamental domain and try to ask what happens to these measures as t goes to infinity. And the sort of the equidistribution theorem tells you that in the limit, these points visit every point of every bit of the fundamental domain with the expected amount. Maybe let me say something at this stage, which is that this theorem has, if you ignore the error rate for a moment, it has a fractal measure on the left-hand side, but no fractal really on the right-hand side. And this is the reason why the Khinchine theorem looks the same no matter what the fractal looks like. Because if you substitute for phi some kind of an approximation of an indicator function of a cusp, that tells you the mass of the set of points which are approximated by rationals whose denominator is of certain size. And this theorem tells you that no matter what the fractal measure is, as long as it satisfies our hypotheses, the mass of all of these, with respect to any of these fractal measures, the mass of these sets are asymptotic to the volume of the cusp, which has no fractal in it. And this is why the Khinchine theorem somehow does not depend on the fractal, at least for our fractals. So maybe let me give you somehow one slide of sort of a summary, a quick summary of how the proof of the equidistribution theorem goes. This is where somehow the two words in my title, two other words in my title come into the picture. So the rationality hypothesis is necessary for our strategy to even get off the ground. And we use this rationality to construct a random walk on an S-arithmetic cover of our homogeneous space, which means it's a product of real and p-adic groups, which, and the random walk is simply a finite set of matrices. You pick one of these matrices to move in your homogeneous space according to your probability vector. And they come from the IFS in a certain way, from the iterated function system. And the rationality of the IFS is what allows us to do this, because if the p-adics, the p-adics that we consider, the primes that appear in those p-adics come from the prime factors of the parameters in your iterated function system. When you have a random walk, you have a sort of an evolution operator, an averaging operator on any space of functions on that S-arithmetic space. And a key ingredient in what we do is that we prove that this averaging operator has a spectral gap on L2. Meaning if you apply iterates of this operator to an L2 function with mean 0, it decays, its norm decays to 0 exponentially fast with an explicit rate. And finally, so this arithmetic space, it covers our homogeneous space, SLNR mod SLNZ, with compact fibers. So there is a good relationship between the two. And what we do is on the homogeneous space, we replace our fractal measure with an absolutely continuous approximation. This is nice. This can be done. It's very easy. And what's known is that if you have an absolutely continuous measure on a horocycle and you push it down like this under the flow, it will equidistribute. However, remember, there's no free lunch. We can't just approximate because the approximation is happening along the unstable manifold of the geodesic flow. So your errors in order to get something meaningful, your error of approximation will blow up. And what we do to sort of battle this error in the approximation is we use the spectral gap and this additional invariance of this operator, which, by the way, I forgot to mention, has a very crucial property. It leaves your fractal measures, these measures mu sub t, invariant. When you lift them up to the S-arithmetic space, it leaves them invariant. So remember, we had some fractal measure, it had no invariance by anything. I take its limit and it has no right to be invariant by anything in the limit. And a key point is that we construct this operator which leaves it invariant, which in particular will tell you the limit will be invariant under this random walk. It will be stationary for this random walk. And we use the fact that, and this construction is valid for any fractal that has rational parameters. And we use the fact that we have this additional invariance with an operator that has a spectral gap to somehow beat the error in approximating by an absolutely continuous measure. In this very last step is where our sufficient thickness condition comes in. So everything works up until this last step where when you're balancing the error in the approximation with your spectral gap, you really need your fractal to have this additional assumption. And I threw in here sort of Silberg's 316 in the slide because well, it's one slide, and I wanted to say that somehow along the way, what we actually really need is equidistribution of absolutely continuous measures on horocycles like this, but with a uniform rate and a uniform errors, completely uniform over any congruence covers of our homogeneous space, over any congruence cover. So I'm pretty sure the slide made a lot of sense. So let me sort of in the remaining couple of minutes, just say a few words about the methods that people use when studying Diophantine properties of fractals and why I feel like it's a very rich sort of subject. And these kinds of methods, they are very, very rich. So there's prior work by Einsiedler, Fishman, Shapira, who proved sort of a weaker form of the result I stated here. But the result I state here is due to Simmons and Weiss in 2018, where they prove that if you take these fractal measures, which are on horospheres, remember they are, I'm pushing them by the geodesic flow. If you add an additional averaging in the flow parameter, then they prove that these additionally averaged measures converge to the Haar measure on G mod gamma without any additional assumptions. No rationality, no thickness, nothing. However, their proofs, the results are not effective. You do not get a rate of equidistribution. Moreover, the methods that go into the proof, for example, the first group of authors, they rely on a measure classification theorem due to Lindenstrauss. It's a very deep result of his work on quantum unique ergodicity conjecture. And for the second group of authors, they generalize Benoit-Kahn's measure rigidity theorems. And because these results are measure classification results, they are inherently not effective. And so we do need to go another route, completely different route, in order to get our results. And an extra thing that I like about our result is that the extra averaging in both of these works are in this time parameter is absolutely necessary. It cannot be dropped. Whereas for us, it's somehow we naturally don't need it. And then in the sort of final maybe minute or two, I'd like to put our ignorance on display. So I'd like to pose, there are a lot of questions. For example, the first question maybe that pops into someone who hasn't fallen asleep yet, and their head is, well, how far can you improve this epsilon zero? Can you go all the way? Is it an artifact of the method? So these are all great questions and one can think about them as well. But let me put a few questions that just really put our ignorance on display here. So we construct this random walk and we say that it leaves any limiting measure of our fractal measures stationary in the limit. And in fact, it leaves our fractal measures stationary. So one can ask a simple question: what are all the stationary measures for such a random walk? I didn't even tell you what it is. It has a simple definition, but what are all the stationary measures? So can we classify all of them? And that's a good, nice little question, which I think is quite difficult, but I think it ought to be very interesting. Notice here that there is not going to be an answer. Familiar with Benoit-Kahn, they tell you for their random walks, every stationary measure is invariant. It's actually invariant by every matrix in your averaging operator. Here we know there are measures which are only stationary but not invariant. So in the language of Furstenberg, these random walks are not stiff. So even the list of stationary measures ought to be a little bit more, let's say, interesting, if such a classification is possible. Secondly, what happens with if you drop the assumption that you have finitely many maps in your IFS? A lot of the time, there are many results out there where you can simply just drop it. You just stare at the proof and you notice you don't need the finiteness assumption on the number of maps. For us, it's absolutely crucial because our error term, this big O, depends on the number of prime factors that appear in our maps. And that's actually kind of upsetting to me. And so one can ask, so what happens? What happens if you allow infinitely many primes? Can you get a similar result? And finally, really finally this time, we do leverage some kind of condition on the parameters, which is not often something you see in the literature. We do impose this rationality assumption on the parameters and get something out of it. Well, maybe even if you're less ambitious, maybe if you don't want at all like Khinchine theorem, can you do something if you impose some extreme condition on the parameters? Can you say anything beyond what's known if you know that the parameters are, say, Liouville or algebraic or badly approximable or whatever it is that whatever it is property that you like to work with? And that, I think, is a very interesting direction. And that's the end of my talk. Thank you very much.
Thank the speaker. We have time for one or two questions. Does anybody have one?
I have a question.
Yes. Hi.
So the fractals you're looking at are self-similar in nature. I mean, they involve rotations and contractions by factors, and that dictates the particular one-parameter flow you have. You have this function g of t. But if you had something that was self-affine, like, for example, a Bedford-McMullen carpet, very fashionable things, could you choose a different one-parameter flow and still prove something?
So the diagonal flow is actually dictated by the Diophantine problem we're looking at. And so that diagonal flow comes from the Diophantine property, from the from the Diophantine problem. So one can ask two questions: can we work with self-affine, or can we work with other diagonal flows? So let me answer the other diagonal flows, self-similar or any kind of fractal. So for self-similar measures, most of our proof of the equidistribution theorem, at least, goes through pretty straightforward if there are no rotations, or in particular, if your rotation matrices commute with, so let me sort of back up 1 second. So this diagonal flow has a block, which is d by d block on the upper left. So you can ask, well, I can put like some different sort of eigenvalues there. As long as this diagonal flow commutes with the rotation matrices, which are also d by d matrices that you have in your definition, then our proof sort of, it goes through. The second part of the question about self-affine fractals, so that's an interesting question. I don't know if I can take it all the way to Khinchine. It's quite delicate to go from the equidistribution to Khinchine, or to get anywhere after the equidistribution theorem. The convergence case follows immediately from the equidistribution theorem, but the divergence case is quite delicate. The equidistribution theorem, one can construct an operator. It's very, one can define it. It's very simple to define. I believe the spectral gap part of our result can be proven also for these operators. And I think the rest of the equidistribution proof should go through. What I could get scared of is not the usual things that people get scared of when studying self-affine fractals, where just studying their fractal properties is a very challenging problem. These problems do not show up for us, but rather that the affine the linear part of the affine maps is not contained in a compact group, and that that may screw up some of the arguments. That I'll have to think about a little bit harder. But that's my only fear, not all the other fears of self-affine. Yeah, sorry, it's a long answer.
Okay, thank you.
That is all of the time that we have for questions in this session. So let's thank Osama again.
Thank you all for coming.